Dr. Tishan. In this video, we are going to look at a Calculus 3 topic that uses Lagrange multipliers to find extreme values of a surface. We're going to do two examples with two constraints in this video. So take a look at the Lagrange multiplier two constraints system of equations we're going to generate here. This is an application of partial derivatives. So we're going to, on the left side of the equation here, take partial derivative of our surface, and we're going to set that equal to the right-hand side. You can see where the introduction of the Lagrange multipliers, the lambda and the mu Greek letters are the Lagrange multipliers. Lambda gets multiplied by the partials of our first constraint with respect to x, y, z. We add to that mu gets multiplied by the partials of the second constraint with regards to x, y, and z. So we're going to set up a system of equations. We're going to have the three equations with the partials of the function's constraints, and then we also have the two constraints. We're going to have 5 equations to use in our system of equations. We're going to try to solve those to find our critical points is what it's going to do. Introducing lambda and mu make it easier, I guess, to find our critical points. We still have a lot of algebra to do, but it'll help us develop another method to get our critical points. So let's take a look at our first example. Our first example, our function is going to be x squared plus y squared plus z squared. There's our surface, right? There's our multivariate surface. Our first constraint, we'll call this our g constraint, will be x minus y equals 1, all the variables to the left and the constant to the right. And then our second constraint, we'll call that y squared minus z squared equals 1. All right, so we want to go ahead and figure out where and the surface within these two constraints is the highest and lowest points, our max value and our min value. So let's start by setting up, and I jotted down the formulas are over on the screen over here. Let's start by setting up our system of equations using the partials and the Lagrange multipliers. So we want to take the partial of our function with respect to x, that's 2x, set that equal to lambda times partial of g with respect to x, that's going to be 1, okay? And then we're going to add to that the mu times the partial of our h with respect to x. We don't have any x's there. So there's our first equation. Okay, so we got to go generate our next one. Let's do the partials with respect to y on the function. It's 2y, multivariate function, all right? Is lambda times partial of g with respect to y, which that's negative 1, all right? And then mu and partial of h with respect to y is 2y, all right? And then let's take our partials with respect to z, partial of our multivariate function with respect to z, that's 2z. All right, and then equals lambda times partial of g with respect to z. Well, that's going to be lambda times 0, all right, plus mu times the partial of h with respect to z, negative 2z. So, and then with that, we have our constraints. So you have the x minus y equals 1. We have y squared minus z squared equals 1. All right, so we have to solve this system of equations. We're going to solve this system. We have all 5 of these to use at our disposal to figure out where our critical points are. So let's see if we can simplify this a little bit. What do we have right here? Because mu times 0, so we have lambda equals 2x, okay? So lambda equals 2x for this equation. Simplifying these up a little bit. So here we have 2y. So 2y equals a negative lambda, okay, and then plus 2, and then mu, and then y, all right? And then this equation here, lambda's gone because it's times 0, so we have 2z equals, and then over here, negative 2, and then a mu and a z. We have this, all right? So let's see what can we do here, and then we have our constraints at our disposal as well. So we want to see, let's see, which one can we utilize, and you got to really look hard at these, but I think what I'm seeing right here, I'm going to use this equation right here, okay? I'm going to use this one right here, all right? So what do we have? So I'm going to take the 2z equals negative 2 times mu times z, and I'm going to add this to both sides. So I have 2z equals, not equals, I'm going to add 2 mu z to both sides. So plus 2 times mu times z equals 0. And I can factor a 2z out of each of these terms. So take out a 2z, and I have 1 plus take out a 2z mu, okay, equals 0. So what do I have here? When is this quantity equal to 0? When z is 0, okay? And when mu is a -1, so I have this right here, okay? So I found what z is. I've got z, that's a keeper, okay? So I found z. Now, is there anything I can do here, given my constraints as well? Is there anything I can do with z equal to 0 to possibly find my x and y, okay? Well, yes, what we can do is we can go to this constraint right here. So what you want to do is try to see if you can't break these down. All right, you just try to figure out if you can find x, find y, find z. And it's a massive system of equations. There's a lot of algebra to think through here. But I found that I use this, and I got z equals 0. So z equals 0, I can plug that in, and I can get my y, okay? So when z equals 0, all right, I'll write it here. So when z is equal to 0, I have y squared minus z squared equals 0. So plug in 0 here, so y squared equals not 0, equals 1. Okay, y squared minus z squared equals 1. So y squared minus 0 equals 1, so y is plus and minus 1. All right, so I know what y is. So when z is 0, I know what y is. All right, so when z is 0, I've got my y. Running out of space over here, so let's come on over, okay? All right, so I have when z is 0. All right, so I have z equals 0. When z is 0, y equals positive 1, and y equals negative 1. When z is 0, my y is 1 or negative 1. I plugged in 0, y squared equals 1, so y is plus or minus 1. What about my x now? Well, x minus y equals 1. All right, so x minus y, so x minus y equals 1. So when I plug in 1, I have x minus 1 equals 1. So add 1 to both sides, x equals 2. All right. So, and then when y is negative 1, what's going to happen here? X minus y equals 1, which, let's see, now I'm going to plug in negative 1 for y, x minus a negative 1 equals 1. So this implies that that's a positive 1, subtract 1 from both sides, x is 0. All right, so I have found my critical points. Okay, I have found my critical points. I have 2 of them. I have 2 ordered triples for my critical points. I have 2 of them. All right, z is 0 for both of them, okay? When z is 0, y is either 1 or negative 1, okay? So when z is 0, y is 1, x is 2. All right, when z is 0, y is negative 1, x was 0. These are my critical points right here, all right? So one of them is going to be a maximum value, one's my minimum value, and how do I know which is which? I go back to my function. All right, and let's find my function value at 2, 1, 0. Well, let's figure out what that function value is, and let's find my function value at 0, negative 1, 0. These are my critical points. So plug these numbers in, so you have 2 squared, okay, plus 1 squared plus 0 squared, so 5. And when you plug in 0, negative 1, 0 to my function, you have 0 squared, and a negative 1 squared, and a 0 squared, so you have 1. Okay, so your maximum value is 5, your minimum value is 1. So your maximum value is when x is 2, y is 1, z is 0, so it's 5, okay? And then your minimum value is when 0, negative 1, 0 is 1, all right? So here is your solution using Lagrange multipliers, okay? So this is your maximum value. All right, and then this one down here is your minimum value. Let me write that in. So this is your minimum value. All right, so using Lagrange multipliers with 2 constraints. Lagrange multipliers with 2 constraints. The first thing you want to do is set up your system of equations. Using the Lagrange multipliers, set up your system of equations, okay? And then what you have to do is you have to take the system of equations and solve, all right? And by the way, we probably should investigate the mu equals -1 as well. If you do investigate mu equals -1, you're going to get a solution. It doesn't work. You're going to get a z squared equal to a negative value. So I don't have space to show that on the board, but the mu equals -1 didn't go anywhere. So we could just kind of ignore that for now, but you should still investigate it. But you're setting up this system of equations. You've got your 2 constraints and then your 3 other. You've got a system of 5 equations, and you're going to use these 5 equations. Your job is to figure out the critical points. Figure out algebraically what the critical points are. You know, you might have to look at it pretty hard to see where it's going. Okay, so here's one technique, and this is not the only one. This is just the one that I saw right now. So you can play around with this and see if there's another way to find these critical points. All right, let's do one more example. Let's do an example where we only have 1 critical point instead of 2, and we have to figure out, is it a max value or is it a min value? So let's do one more example here. I'm going to erase this one. All right, and let's just take a look at one more example. So in our second example, instead of having 2 critical values, instead of having 2 critical points, one was a max, one was a min, we're only going to have 1 critical point. So if you only have 1 critical point, then how are you going to determine if it's a max value or a minimum value? So we'll take a look at how that works. We're going to take a look at how that works in our example number. Look at example number 2. So example number 2, our multivariate function for example number 2, our multivariate function, it's going to be a function of 3 variables. It's going to be x times y times z. Okay, subject to 2 constraints. Subject to 2 constraints. So our first constraint is going to be x plus y plus z equals 32. And our second constraint is going to be x minus y plus z equals 0, subject to 2 constraints, okay? So we want to start, okay, well here, and this will be our first constraint is our g constraint, okay? So we should label that with a g. And then our second constraint is going to be referred to as h. And just make sure your variables are on the left and then the constants on the right. So let's go ahead and set up our system of equations. We're going to introduce lambda and mu to help us generate our critical points. This is what we do, is we now introducing lambda and mu. It's a five-part system of equations to solve, but it usually makes things easier to see. So let's go ahead and set up our system of equations. We want to take partial with respect to x, okay, then hold the x as a variable, y and z constant, gives us y times z, okay? Partial of, so lambda times the partial of g with respect to x is 1, plus mu times partial of h with respect to x is also 1. Then let's do partial with respect to y's, okay, of the function. Then partial with respect to y is going to be x times z. That's going to be lambda times the partial of g with respect to y, which is 1. And then the lambda, mu times the partial of h with respect to y, that's a -1. All right, and then finally our partial with respect to z multivariate function is going to give us x times y. That's equal to lambda times partial of g with respect to z is 1, plus mu times partial of h with respect to z is also 1. So we have our system of equations here in terms of lambda and mu. Don't forget, we also have the constraints at our disposal. X plus y plus z has to add up to 32, and we know that x minus y plus z is going to give us a 0. All right, so we want to solve the system of 5 equations to find our critical points, okay? So to find our critical points, all right, I'm going to take my lambda and mu equations and simplify them a little bit. So what really do I have here without all the grouping symbols? Y times z equals lambda plus mu. What do I have here? I have x times z, x times z, okay, equals lambda minus mu. And then what do we have here? We have x times y equals lambda plus mu. All right, so we have this, all right? Now, what do we see? Can we see, and you gotta look at this, you gotta look really hard and see, because we want to figure out a method that we can use to solve to get our points, all right, our critical points, so we can figure out how to classify them as maxes or mins, max or min values, all right? So looking at the expressions in terms of lambda and mu, I see lambda plus mu in 2 spots here. Lambda plus mu is y times z, lambda plus mu is x times y. since lambda plus mu gives me y times z, and lambda plus mu gives me x times y, well then I can set the y times z equal to the x times y, because they're both equal to the same quantity. And so look at this equation here. So if y times z and x times y are equal to each other, y must equal y, so z must equal x. And so I have a relationship. I don't have numbers yet, but there's a relationship. All right, so that's the first thing. That's what I saw over here. So the lambdas and mu's help me see that. All right, now something else we can do. Let's see, something else, you know, because you have the constraints that you can work with also. So look at the constraints, all right? We can take these constraints and we can just like add these together. Let's go ahead and add these constraints together. Just add them together. The y's are going to drop out. So add the x's because you have the system to solve. And you can do whatever you need to do. The y's drop out. Add the z's together and you have 2z. 32 plus 0 is 32. You can divide every term by 2. So you have x plus z equals 16 when you divide by 2. X plus z equals 16. My lambda mu equation over here, x and z are equal to each other. Well, if they're equal to each other and they add up to 16, we know what x is, we know what z is, okay? So x plus z equals 16, all right? So that means that x plus, well, we know that z and x are the same thing, so x plus x must equal 16, all right? 2x is 16, so x must equal 8. And x equals 8, well, that means z is equal to 8, okay? So what do we have right now? So what we have right now is we have x equals 8, we have z equals 8, right? We know what x is, we know what z is, we just have to find y. How do you want to find y? It doesn't go back to one of the two constraints, they'll both take care of it for us, okay? So x plus y plus z, what does that add up to? 32, all right? So 8 plus y plus 8 equals 32, so y equals 16. X is 8, z is 8, y is 16. There's our critical point, okay? So we've got our critical point, and so introducing lambda and mu, our Lagrange multipliers, help us, even though it's a 5-part system of equations, so the algebra can get tricky, it can, all right? But it helps us to see where our critical points are. So we've got our critical point, all right? Our critical point is going to be 8, 16, 8. There's our critical point, okay? So this is our point right here. And now we want to, let's figure out what the value is, okay? So we have f of 8, 16, 8. Okay, well that's equal to 8 times 16, right, times 8. Okay, so when we multiply that out, we get 1,024. Okay, 1,024. Now we only have the one critical point. We only have the one critical point. So we have to, is that a maximum value or a minimum value? We have to classify this. Okay, so we have to classify this. So how do we classify, is this a maximum or minimum value? Okay, that's our big question right there. Is it a maximum or minimum value? Okay, so determine if it's a maximum or minimum value. We need to choose. We need to choose a point, all right, that satisfies both constraints at the same time. We need to think of something, all right, what are the constraints? So we need to think of 3 numbers that add up to 32, and then x minus y plus z. We need to, what do you have? What do we have that satisfies both constraints at the same time? And you just have to think of something that might possibly work, okay? I've got something in my head, 16, 16, 0, I believe works, okay? 16 plus 0 is 32. 16 minus 16, 0 plus 0 is 0. That works, okay? This works in both constraints, so let's test it, okay? So plug in 16, 16, and 0. So what is 16 times 16 times 0 when I plug it in? Ooh, well that's equal to 0, isn't it? Okay, so that's equal to 0. So my test value generated a number less than what I have here. So because my test value is less than my critical value, then my critical value is going to be a maximum. My test value came out less, so I found a maximum value. So your final answer here is your maximum value is 1,024 is your maximum value. That's your maximum value, 1,024. And the critical point where it's found is at 816.8 on this function, subject to 2 constraints. So this is what happens when you only have one critical point. Then you're going to have to think up. There's probably infinitely many points at work in here, but it's a little bit harder to think. You've got to think up a test value point that works in both constraints simultaneously, at both constraints at the same time. Right? Once you find a critical point that works in both constraints, plug it into your function. If your test value comes out less than the critical number value, then you found a maximum value. If your test value comes out greater than what your critical point value comes out to be, then you found a minimum value. Okay, so here is Lagrange multipliers with 2 constraints. Okay, so the hard part, obviously the hard part is solving that 5-part system. Okay, so the algebra with solving that 5-part system is the hard part. You're introducing lambda and mu into your system of equations to try to help you see where those critical points are. All right. Whew. All right. So I hope that helps with this topic if you're working on it now. So that's all for this video. So thank you so much for watching, and take care, everybody.